Three concentric circles have radii 1, 2, 3. An equilateral triangle with side length s has one vertex on each circle. What is s squared? Okay, so this is a geometry problem. So we should start by drawing a diagram. So I'm going to freehand the circles just like you would do in a competition. So, they won't be exactly the neatest, but always make sure to try to draw your diagrams as to scale as possible. Because it'll help us with figuring out where points are, like within or outside or inside the triangle. You'll see what I mean by that. So here we have our center. I'm going to call this point O. And we have, this is distance 1, this is distance 2, this is distance 3. Okay? And now we can imagine what would it look like to have an equilateral triangle with one vertex on each circle. So we can imagine, okay, we have like one vertex here. Maybe we choose the other one here. Oh, well, the third vertex is nowhere near the third circle. Okay, so we could try again. Maybe we put it here, right? Okay. That actually worked a lot better, right? So we could try like a lot of different points. See, that one doesn't quite make it onto the second circle. If we tried like here, that would be way too far out, not on the second circle. But if we try like this spot, we get like a sort of like Goldilocks zone, right? This looks pretty good, right? So this looks like a pretty good diagram. I'm gonna stick with these 3 points. Okay, so this is our equilateral triangle here. And the key insight with this problem here is, of course, we have to use the fact that the 3 circles have radii 1, 2, 3. So the most clear way we can relate those lengths to the triangle, right? So these are lengths S, S, S. The clearest way we can do that is just connecting O to each of these 3 side lengths or vertices of the equilateral triangle. So we connect that, connect that, connect that. We know that this has length 1, this has length 2, this has length 3. And at this point, you can realize, wait a minute, we don't need the circles anymore. We just don't, right? The circles serve their purpose. All the circles really meant is that the distance from the center to each of the vertices is like 1, 2, and 3. So we can get rid of the circles and just draw the like full diagram. So once again, looks something like this. 1, 2, 3. So in particular, by drawing this diagram here, like close enough to scale, we see that the point O is outside of the triangle. And that makes a lot of sense, right? Because this length 3 here is very long relative to the 1 and 2. And this is going to help us a lot in figuring out the problem. If you accidentally got that the point was inside the triangle instead, it wouldn't prevent you from solving the problem, but it would make things more confusing. You would have to figure out later on in the problem, you would get like some weird like negative length and then realize that, oh, you need to like flip it. You need to put the point outside. But by drawing a nice diagram, we see that the point here is actually outside the triangle. Okay, so this is point O. These lengths are all the same. We don't really need to draw that in. In fact, the main key thing here is that all of the angles are 60 degrees, right? That's a common trait about equilateral triangles. And in fact, what we're going to do here to solve the problem is we're going to do a rotation, right? So right now we have these 3 lengths here, 1, 2, and 3. And of course, we know like 1 plus 2 is 3, right? We want to like use that fact in the problem. We want to like line up these lengths with each other in more ways so that we can use them more, right? But like currently we don't really have a lot to work with, right? Like we have like this is X, this is Y. We could do like law of cosines bashing to figure out the lengths or figure out the angles and the lengths eventually, but that would be way too complicated. So instead, we're actually just going to rotate the triangle by this vertex 60 degrees clockwise. And the reason why we do this is because this 60-degree angle is going to really help us find some new lengths in the problem. So whenever you see an angle of a triangle like this, you can think about what happens if you rotate points in certain ways. So in this case, when we rotate it, right, I'm going to call this new rotated point here O prime, right? This is the new like equilateral triangle, right? So we rotated it about this vertex 60 degrees. So in this new diagram, we have that this length is 2, this length is 1, this length is 3. And in fact, most importantly, this angle here, so I'm going to use a different color for this. This angle here between the two lengths of length 2 is 60 degrees. Because we rotated the whole diagram by 60 degrees, this length and its rotated version must also have an angle of 60 degrees between them. And of course, they're also the same length. So this length here must be 2. But now you see, this length is 1, this length is 2, and this length is 3. And as we talked about, 1 plus 2 is 3. So this is actually a degenerate triangle. And this is very helpful for us because what that actually means is that the points are collinear, right? So this rotated version of this point, now that we know that, we can like erase this and redraw it. So basically, when you rotate this length by 60 degrees, it ends up back on the line. So this is length 1, this is length 2, 2, 2. And this is important because this angle here was 60 degrees, right? This is an equilateral triangle, 60, 60, 60. And therefore, this angle is 120 degrees. So now we actually just have a triangle with length 1, length 2, angle 120 degrees. And what are we trying to find? We're trying to find s squared, where this is the side length. This is exactly like we can apply the law of cosines to this. The law of cosines, this is exactly what we were looking for. So we can write s squared is equal to 1 squared plus 2 squared minus 2, 1, 2 cosine of 120. Cosine 120 is going to turn out to be negative 1/2. So this cancels out with the minus 2, and we just get plus 1 times 2. So s squared is going to be 1 plus 4 plus 2, and that's just going to give us 7. So by first we reduced the problem from the 3 concentric circles. We just used the radii to and the center of the circle. So in general, when you have a problem with circles, make sure to draw in the center of the circles and use the radii of the circles to get more length in the problem. And the other thing that we used here is the fact that rotation by 60 degrees, rotating points by 60 degrees is very powerful in general because it creates a lot of equilateral triangles. And that can be very useful when you have like 3 different lengths that you want to like form into a triangle. Okay. After you qualify for AIME, make sure to check out our latest AIME preparation book, the 5 practice tests to consider your Math Olympiad, to continue your Math Olympiad journey. And you can explore our full collection of AMC preparation books on MathTopia Press on Amazon, which include full practice tests and detailed solutions.